All right, let's take a look at the big rules of differentiation that we're going to be using during this class. But first, let's quickly look at the derivative. We're going to look at this in more detail during class, but here's sort of the big idea. We're trying to estimate the slope of this function at some point. We can't actually figure out an instantaneous rate of change. Right? Fundamentally, what we want is essentially a line tangent to that point on this function. Something that's just touching this, and we can talk about the technical details of that. But what we're going to use to get to that is the derivative, which is this limiting function. So we take something that we can do, which is measure the slope between 2 points. So we take x, we say here is f of x, we add some arbitrary number to that, right? We're calling it h here. Sometimes you'll see it referred to as epsilon or delta x. The term doesn't matter. What matters is we're nudging x around, right? And we're calling it a positive nudge, but it could just as easily be plus negative 0.5. It is some number. We're just varying the value of x a little bit and asking, based on that little change, going from x plus h to x, what is the difference between those two values? And the output values, we end up with f of x when we have x. When we put in x plus h, we get f of x plus h. So now we can measure our rise over run slope, right? Our change in y, this is what we really care about. Our change in y is this distance up divided by our change in x, this distance across, rise over run, there's our slope. Now this is obviously a pretty bad estimate for the slope of this particular function, and that's why we have this limit. So we make x smaller. All right, so we've got some x here. Maybe we look at a -1 really quickly, and we look at the slope there. That's pretty close to what we're looking for. That is still not the full thing. That is really just saying that arbitrarily is a better estimate, right? If we look from here to here. We can do that as a human being who can look at a piece of paper and interpret the math, but we want to be rigorous. We want to make sure that we're really getting down to the heart of the matter. And we're going to see with these rules of differentiation, which again, we'll dig into in more detail. With these basic rules, we can actually get what happens right at that point. We're getting infinitely better estimates until, at least in the limit, under certain conditions, this is going to be the actual slope at this point. That is going to be, I'm going to do as good a job as I can, the slope dy dx. Oops. dy dx, not dx dy. So that's what we're doing. Let's take a look at these functions. I'm going to do them in a slightly different order than other people do, but just to build it up as we go. So with the simplest case, the constant function rule, what we're looking at is a function that looks like this. We've got some x, we've got some y. We're saying y equals 5. What happens if we increase x? Well, at any given point, right? So f prime of x, where x equals 3, well, our slope is 0, right? It's pretty easy to see that. At any point, our slope is equal to 0. So given that this function is just a horizontal line, our slope is 0. Rise over run is, no matter how far we go to the right, we go 0 up. Our linear function rule is almost as easy, x and y, and we've got something like mx. We're going to add in mx plus b in a second. But here, dy dx, this one's going to be really easy. It's just the slope of the line is the slope coefficient. So it is literally just m. And we're going to see also in a minute that we can think about this as a general function of a rule we'll see later. The power function rule, so let's just set ourselves up for that. F of x, where we're looking at, say, m times x to the 1. But we'll come back to that. All right, we've got the constant function rule. Nice and easy. Slope is 0. Linear function rule. The slope is the slope term. Now what about mx plus b? There we have a sum of two functions, or we might think about a difference of two functions. So in the case of mx plus b, let's say b equals 5. We can take this and we can add this value at each point, and that's going to be the equivalent of just sliding this whole thing up by 5. And there, our slope is going to be m again. So when we sum two derivatives, we have this nice property that the derivative of the sum of the functions is just the sum of the derivatives of each individual part. So for mx plus b, we're adding m, we're adding the slope of b, which is 0, so we end up with just m. If we take a difference, so f of x is some function g minus some function h, it's fundamentally the same thing here. We're going to take g prime and we're going to subtract h prime. So if we said mx minus b and we slid it down here, we would still have m as our slope. Right? Parallel lines, same slope. We have the same impact on y or some change in x. All right, the power function rule, we're going to see a lot because we're going to be working with a lot of polynomials. F of x to the n becomes f prime of x equals n. We bring down the exponent times x to the n minus 1. That'll make more sense when we go through when we actually derive that rule, but we're going to use it so much that you're going to forget that anyways. So don't panic too much. N times x to the n minus 1. We're going to do a lot of that, so this is a really handy rule. And we don't need to go through all the effort of calculating a limit, certainly not once we've wrapped our head around it. Now let's come back to mx plus b, right? We can drop the plus b because we know that it's going to be m plus 0, but m of m times x is the same as m times x to the power of 1, which, when we're finding f prime, is going to be the same as saying 1 times m times x to the 1 minus 1, which is the same as m times x to the 0, which is the same as m times 1, which is m. So when we're using a power of 1, the power function rule is consistent with our linear function rule where we just get our slope coefficient back. Now another thing we're going to talk about is second derivatives. Let's do a really quick preview of that now. If we've got the derivative, the first derivative of mx, we could take the derivative of this function also. Now m is just a constant, so it's going to look like this. It says that at each point across x, the slope of this line is m. The derivative, the change in that slope as we change x is 0 because it's a constant. So we could say f double prime of x equals 0. We don't end up with, what would this be? This would be like m. Well, actually, I guess it technically fits in there. M, does it? Let me walk through this. M times 1. We're going to pull down that exponent. Or actually, no. Let me go back to what I was doing. I'm going to do this over here. So f of x equals m times x to the 1. F prime of x equals 1 times m times x to the 0. F double prime of x equals, we're going to bring down the exponent. We're going to have 1 times m times 0 times x to the minus 1. 0 times anything is just equal to 0. Right? Now, that said, it might be tempting to go even further, and I guess we technically could. It would just be kind of pointless. Going further, saying f triple prime of x, we could keep this x and we'd have an x to the minus 1. We're going to have a 1 m times 0 times minus 1 times x to the minus 2, but we still have this 0, and we're not going to get rid of it no matter how deep we go. So past some point, this ends up with a higher order derivative of 0, and that 0 stays. We can't really derive this function any further. But we'll talk about that when we get closer to talking about optimization. Long story short, the power function rule, we bring down the exponent so that now it's being multiplied at the front. So we get 1 times m times x. We knock the exponent down by 1 to 0 in the case of m times x, or n minus 1 if we're thinking about x to the n. The product rule. Here's another one we're going to see a lot. G of x times h of x. So our function is built out of two smaller functions. And it's often going to be the case that it's easier to deal with these smaller functions. So this is a really nice simple rule. This is simple enough that I can even remember it despite having a really bad memory. G prime times h plus g times h prime. And you'll see the order flipped, and this is the really beautiful thing. This is the same as, say, g prime h plus h prime g, which might also be a little easier to remember. The order of these doesn't matter. 2 times 3 is the same as 3 times 2. Right? A plus b is the same as b plus a, so the order here doesn't matter. That makes it easier for me to remember. I know that I've got the derivative of one plus the times the other, plus the derivative of the other times the first one. Right? Product rule, that's another one that's going to come up a lot. So let's generalize the power function a little bit. If we've got k times x to the n, that is really the same as the constant function rule. K is some constant. It's not really a function of x, but we can take the derivative of it. And we're multiplying by some other function of x, x to the n. Now, x to the n, we can use our power function rule, n times x to the n minus 1. Times h of x, which is just k. So we get n times k times x to the n minus 1. Right? That's the same as, I guess, this part. Right? If we think of g of x as k and h of x as x to the n. We're getting this part here, and then we're adding here, well, the derivative with respect to k, well, that's just 0. So plus 0, and we don't even have to do the math at that point. So this form, this example, you'll often see given with the power function rule. I just separated it out just to make it clear that this is consistent with the product rule. And really, we're just saying we're fundamentally doing the same thing as the product rule. But since we got the 0 that cancels out, we're going to be lazy in cases like this and just do this first part. The quotient rule is one where order matters. And so I have a hard time memorizing this, but I have an easy time memorizing the chain rule. So we can look later on at how to use the chain rule and the product rule to derive the quotient rule. This is something that I have often done as an exam question in the past. For an online class, it doesn't quite make as much sense, but it might make sense as a homework question. And we're pretty good on time, so maybe I'll go through that. But let's look at the quotient rule first, and then the chain rule, and then we'll derive the quotient rule from these two. So if we've got f of x is g of x over h of x, some function g, some function h, we're going to deal with these separately. We're going to get a g prime, we're going to get an h prime. But putting them together for g over h, this larger rule is what lets us sort of jump to the overall derivative. So g of x over h of x, we go to h of x times g prime minus g times h prime all over h squared. That's a mess of things. Does the h go on the bottom? Is it a square? Is it a prime squared? Do we subtract g prime h or g times h prime? That doesn't fit well into my head. Now, obviously, I've got it in my notes now, so I could just flip to my notes. I could, attach a little flag to this to make it easy to find on the exam. But I've got finite space in my brain, and I want to put more cool stuff in there. I'm not going to try and memorize this, and I don't even want to try and memorize where it is in my notes. I guess I could look it up on Wikipedia in real life. But it's going to help us to wrap our head around these guys to deal with the quotient rule. And like we were doing with the supply and demand stuff earlier, I'm going to be looking at this very often from the very general point of view, right? Actually figuring this out for G and H rather than a specific function like, say, oh, well, I don't even have it. Oh, like an example here. Here's my specific example. So the chain rule is where we've got a chain of functions where one function is put into another function. And we could do this g of h of x of, or whatever, right? G of h of f of any number of functions, right? Nested functions is what we're dealing with here. Now, another way to think about this is we could think of this h term as some other thing u. So whatever value we get out of h of x is u, right? So it's like y equals h of x, and then f of x equals g of y, right? Or in this case, g of u. So u, 5x squared plus 3, u to the 4 is our fundamental function that we want the derivative of. We want that derivative as a function of x. So another way to think about this is, here's the rule really quickly. We're going to take the derivative of the outer function, leaving the inside untouched, and multiply by the derivative of the inner function. That's not too bad, right? That's something that even I can fit into my memory. But another way to think about this setup is, and here's where Leibniz notation comes in handy, we want dy dx, but what we have is y as a function of u, and we can find dy du. We can also find du dx, right? We can find the derivative of this with respect to x. We want the derivative of this with respect to x, but this doesn't have an x in it. But, nice thing here, du over du, those du's can cancel out, dy over dx. That's what we want to find. So, to find dy du, right, we're not going to cancel them too soon. We're going to find dy du, we're going to multiply it by du dx. And that is fundamentally what we've got here. We've got dy du, and we've got du dx, right? So h of x, again, we're calling u for this example, and u is just some made-up letter, some made-up name for this little function. But let's walk through it. So the derivative, this first part, we're going to get 4 times u to the power of 3. Right? Nice and easy, just a power function rule application there. 4u to the power of 3. The inside, 5x squared plus 3, that has a nice easy derivative, 10 times x. Right? We still have this u here, but we've done all the math we need. Now we just need to substitute. We plug this in, and we get 4 times 5x squared plus 3 to the power of 3 times 10x. It's going to be easy to forget this last piece, right? You're going to be tempted to find just the derivative of this and forget to do this second part. But fundamentally what we've got here is the derivative with respect to u, right? But we've actually plugged in u. And the derivative with respect to x of the overall thing, the dy dx that we actually care about, is the product of this term and the u prime. Right? dy du right here, du dx right here. All right. Now, let's see how quickly I can do this. We're going to use the chain rule. Right, so we'll say f prime, actually let's call it dy dx equals dy du dx. We're going to use the chain rule, and we're going to use the product rule, where we're saying dy dx equals g times h. Let's see, how do I want to do this? Here's where Newtonian notation fits a little nicer. We'll say f of x equals g of x times h of x, and f prime of x equals g prime times h plus h prime times g. Being a little lazy with my notation, just to keep things a little tidier, g prime is just shorthand for g prime of x, like we did right here. And I want to find, well, what if we've really got f of x equals g of x over h of x, right? So I want to find f prime of x. And here's just my cheat sheet I'm using to help me figure this out. So what I'm going to do is I'm going to change this so that I can use the product rule instead of having to remember the quotient rule. So this is exactly the same as g of x times h of x to the minus 1. So now I can find a chain rule on this. I can do a product rule on the overall thing. Let's just really quickly rename this. We're going to call this h tilde of x, which is just h of x to the minus 1. So when we want to find the derivative of this, h tilde prime, that's going to be minus 1 times h of x minus 1 again, which is going to be minus 2, times the derivative of the inside, which is just h prime of x. And then we're going to do just some nice simple product rule stuff with it. So we've got h prime of x, g prime. We don't even need an actual function. We can just say there's g prime. So we want to know f prime. I'm going to switch colors one more time. F prime of x is going to be g prime h tilde plus h tilde prime times g. Right? So we're not using h, we're doing a slightly different version of h. If you've never seen this before, I recommend Googling TV tropes, the world of hats. They talk about a thing that happens in TV shows, or at least used to, where they go to some strange new planet where everything's exactly the same except the characters are wearing hats. That's all that's going on here. We gave a hat to h to make it distinct from the actual h. This h is an imposter, but a useful one. So now what we want to do is we want to plug in all these values here and put it back in terms of g and h. So we're still going to have g prime. H tilde, this is just h to the minus 1. I was going to put that in parentheses, but I don't need to. Plus h tilde, which we figured out, which is minus 1 times h of x squared. To the minus 2 times h prime. Right? I'm condensing a lot of notation here, so let me make this explicit over on this side. Minus 1 times h of x. Minus 1 is just minus 2 times h prime of x. And then I'm just going to be lazy here and say h to the minus 2 times h prime minus 1. We're really just getting a minus here. So minus h to the negative 2 times h prime. And hey, check this out. That minus 2, that's going to do this thing that we want here from the quotient rule. So let's keep putting this together. Now we've got this minus h2, and we're going to want to mash that together here. So let's take this and say g prime h to the minus 1. This is the same as just saying g prime over h. And let's multiply this by 1. I'm going to multiply it by 1 in the form of h over h. This is a handy little trick. Sometimes your setup, you don't see a way forward, but multiplying by 1 doesn't change the value of this term, but it gives us an extra h to work with. Right? So that, let me not forget this, but this is going to turn into g prime h over h squared. And hey, check this out again. There's that g prime times an h over an h squared minus some other stuff, which is what we've got over here. So plus minus, let me just get rid of that plus and call this a minus h prime. This is h to the negative 2, which is the same as h prime over h squared. So we lost a g. Where did the g go? There's the g. I forgot the g moving from this line to this line. So we need a g here. There's that. This is why it's good to check your work as you go, and then again when you're done. So g prime h minus h prime g over h squared. And since they have the same denominator, we can say g prime h minus h prime g over h squared. which is the same as we've got here. Let's double check. We've got an h times g prime minus an h prime times a g all over h of x squared. Cool. So we got this by using the chain rule on a different version of h, which allowed us to change this from a quotient, from something divided by something else, into something multiplied by something else. That added a layer outside of this extra exponent, which meant we needed to use the chain rule to get the derivative of this. But we were able to use the much easier to remember product rule and then the relatively easy chain rule on just one small part of that. And putting that together, we get back to our quotient rule, which, like I said, the order matters here in a way it doesn't matter for here or here. G times H or H times G is exactly the same. As you've seen, I'm flipping them back and forth all over the place. That's just, they go on the page, right? What order they go in doesn't really matter to me, and my brain just doesn't want it to. Maybe your brain works differently when it sees this stuff and the quotient rule is easier, but for me, this is just what fits into my addled brain. So, quotient rule, the order does matter, right? So we've got something minus something. We need to subtract the right thing, right? Remembering what it is, well, you have your cheat sheet. You don't really need to remember. But we can, again, just see that it is consistent with this overall set of rules. All right, so this is sort of a reference video. These are the rules. We've seen them all one after another. What's going to be more important is practicing those rules, which is what we're going to spend today's class on.